Hello, physical geographers. We're going to get into the hydrosphere, so this should be a relatively straightforward chapter. Talked about climate change last chapter, so we'll kind of delve into waterland, if you will. Okay, so hydrologic cycle. We talked about quite a bit of this in early chapters: surface area, water movement, air to surface. We talked about change of states, which really kind of set up the later parts of the class before we got into weather systems, and then severe weather. We talked about those things, so it kind of fits in here. And energy transfer and hydrologic cycle. So movement of ocean waters, tides, ocean currents, waves, permanent ice, permafrost. So that's where basically water changes state and freezes, and it can get to very deep, very low temperatures. And surface waters, lakes, wetlands, rivers, and streams. So wetlands are key because that's how the groundwater naturally cleans itself. Groundwater movement and storage of water, zone aeration, saturation, water zone, groundwater mining. We'll get into those. More than 99% of the Earth's water is stored in oceans, lakes, rivers, glacial ice, and rocks beneath the surface. Remaining 1% is in a continuous sequence of movement and change, the hydrologic cycle, which that's where essentially water moves different states between different environments. So surface to air, here's our hydrologic cycle. We've seen some diagrams like this earlier. So essentially we have moisture moving up in the air, evaporating. We also have some evapotranspiration. We have precipitation occurring. In this case, it's over the mountains. If we have basically a front, we called it previously a parcel of air forced over the mountains. Essentially, we can have moisture that precipitates by the air temperature dropping, and lo and behold, we have moisture and runoff, or water that can permeate through the ground, becoming groundwater, and so forth. Air to surface, basically the water can heat up and turn into a gaseous state. Okay, so 86% of all evaporated moisture comes from the oceans, 14% from land surfaces, 78% falls in the oceans, 22% on land. Really interesting. Good breakdown. Runoff. So if it doesn't permeate, doesn't evaporate, it's runoff. Residence time. So essentially wide variation in times individual molecules of water move through the hydrologic cycle. So when does it change state? Where does it change state? Notice we talk about the world ocean in 5 parts. We have 4 oceans: Pacific, Atlantic, which we'll see on the west coast and east coast respectively, Indian, and then Arctic, which we see toward the south. Some great globe diagrams off to the right here. Okay, Arctic Ocean breakdown: 4%, Pacific 45%, Caribbean Sea, key waterway, Mediterranean Sea. We talked about Mediterranean climate last chapter. Indian Ocean is about 20%, Southern 6%, which isn't an ocean, it's more of one of the 5 regions we talked about. And then we have the South China Sea too. So Sea of Japan is also another key waterway. Seems to be in the news a lot recently. Okay, ocean composition. So salinity, it's different from what we call freshwater. Salinity is essentially the ability of salt concentrations to exist in the water, and then we also have carbon dioxide absorbed by the ocean, which we talked about last chapter, affecting climate change. And essentially absorbed by the ocean can create carbonic acid. So we can have acidic situations which can affect life. For instance, marine animals like shells, seashells, also algae, plants, vegetation, so forth. Ocean temperature. Essentially, seawaters can decrease with decreasing latitude. That's pretty straightforward why that occurs. It has to do with insulation and effects on the ocean. And it tends to be different densities. This can be affected by the water temperature itself and also what's in the water in terms of salinity and CO2. Tides are bulges in sea surface some areas. Sometimes we see the tides moved by the sun and the moon. that causes the water to move at different levels. Two bulges form on opposite sides of the planet. Coastlines move in and out as the Earth rotates. Okay, so we talked about high tide and low tide, which is flood tide and ebb tide, respectively. We have movement of ocean waters. Tidal range, which is the difference in the elevation between these two. And here's some examples of the tide and normal tide and spring tide based on where the Earth is. Spring tide higher than usual. Tides on sun and moon are aligned, so that's the gravitational pull we talked about. Neap tides lower than normal when sun and moon are at right angles to one another. So we don't have, the more mass we have, the more the water is pulled by gravitational pull. We're going to do a little bit of physics here. Okay, and then we have variations of tide too. Tidal bores, walls of seawater push up river for enormous tidal inflow. So it's essentially a tide that's going higher than the water flowing into the larger body of water. Then we have a thermal line circulation, slow circulation of deep ocean water of different densities. The densities affecting the water that moves, and essentially global conveyor belt circulation, combined pattern of surface currents through thermal line circulation. So we see that kind of movement based on density of the water and what's in the water, salinity and temperature. Also, I do believe CO2 affects that a little bit. Okay, the permanent ice, we talked about the cryosphere. Ice about 10% of the Earth's surface. There's a lot of concern with climate change of that diminishing. Names of oceanic ice pack, extensive cohesive mass. Definitions are on the slide here for you. Ice shelf, massive portion of ice sheet over the sea. Flow, large flattish mass of ice broken from larger body. That would be a little bit more of a concern, like an iceberg, which is our last item here. Permafrost, large body of frozen subsoil or ground ice. Thawing of permafrost, some documentation and some charts here is concerned about that thawing in addition to polar ice caps. Surface waters, it's only, 0.02% of the world's total supply is essentially what we usually call lakes. So we have some large lakes, Dead Sea, Mediterranean Sea, our Great Lakes. Saline lakes are non-oceanic saltwater. We have the Great Salt Lake in Utah. Ephemeral lakes contain water only sporadically or dry most of the time. Okay, then human alteration in natural lakes. We see this through dams, like we have at Mead Lake that dams up the Colorado River, through the Hoover Dam, which we see a picture of right here. Quite a sight to see if you ever get a chance to visit it. Actually, my client presently, for my 8 to 5 job, I do quite a bit of work for Colorado River Agency, which basically their water supply feeds from there is a very large hydro system, hydro dam to generate energy through that region, through Arizona and so forth. Okay, wetlands, land areas saturated with water, filter surface runoff, very key because this is how nature cleans itself in terms of water. Swamps, mostly trees, marshes, mostly grasses. And then surface water is generally, we call this running as a stream. Drainage bases, then we have groundwater, which we use heavily in addition to piping water over the Continental Divide in Colorado. We use groundwater pretty heavily to supply the mass populations we have on the Front Range or eastern side of the state in Colorado to provide us water for drink and cleaning and so forth. So aquifers, aquifers, moderately permeable rocks, aquicludes, underlying materials hinder or prevent water's movement. So it's kind of isolated, like it's its own pocket. And then we have zone aeration, mix of solids, air or water, so water mixing up, zone of saturation, all places in soil cracks filled with water. The water table is how high is the water that exists in the what we call the water table. How high is the groundwater, which is basically when people drill for wells, that's basically what the water table is. You need to drill the well beneath the level of the water table. And we have confined aquifers, piezometric surface, elevation, groundwater will rise under natural pressure. So if there's any pressure that's happening in the soil from other means, it could be all kinds of things, geologic activity, it could be construction, it could be increased mass from a catastrophic event, it could be all kinds of things. Okay, groundwater, cone of depression, basically if the ground underneath the water can't hold it, it basically will cause the ground to sink. Groundwater mining, essentially bringing up the water to the surface. You also see that with fracking, trying to bring oil and gas out of the surface. And then groundwater extraction, also subsidence or shrinking of surfaces, is used. Ogallala Aquifer, largest aquifer in the United States. Extraction started in the 1930s. Rapid expansion of crop irrigation, causing the water table to sink even deeper. There was a really interesting story on 60 Minutes that talked about using satellite imagery and certain types of infrared signals to determine how much water we're losing on mainland. Really interesting. Try to post that for you all. Ogallala Aquifer spans a huge area, Colorado, Nebraska, down through Texas. Very large concern. So I hope you found that interesting, and we will be talking a little bit more about climate change, getting into some landscapes in terms of finishing up the class, and so it'll be a little bit simpler, kind of like this hydrology, hydrosphere chapter we talked about. Hope you're keeping up with everything and hang in there this semester. Thank you.